All right, so now referring to number 6, question A, we've got HPO4 2-. So you want to go over to the appendix. We're going to be looking at this one, okay? Notice you've got Ka1, Ka2, Ka3. This is for the first proton dissociation, second dissociation, third dissociation. And now I've written it down on my sheet here. So the first dissociation, losing the first proton, Ka1. And you can calculate the reverse of the Kb. The second dissociation, Ka2, losing another proton. The Kb2 is that way. And then Ka3, the last dissociation, and Kb3 as well. So the question is asking us to find the Ka of H2PO4. Okay, so HPO4 2-, the Ka of it would be this way, okay? So the first dissociation, the last dissociation, it would be Ka3 value. So that would be, when you look at the table, the third Ka, 4.2 times 10 minus 13. Okay, so that is the Ka3, the value of it losing that final proton to become phosphate. Then the question says, in brackets, Ca, its conjugate acid is the opposite way. Okay, so its conjugate acid, so if now HPO4 2- is acting as a base, its conjugate acid would be this way. Okay, so now it's, as an acid, it works that way, Ka3. But when it's a base, its conjugate acid is H2PO4. So you have the Ka value for the second dissociation as it works this way. They want you to give the Kb value in the reverse. So the Ka value for that, you would look at Ka2, which is 6.2 times 10 minus 8. Now you have to calculate the Kb. That's what we want. So you would calculate this, Kw divide Ka equals Kb, which equals, I don't know, I don't have my calculator with me. Then to decide whether this ion would rather act as an acid or a base, you compare. Is the Ka value, this one, larger than this Kb value? So whichever is larger determines the affinity for this ion to either behave as an acid or behave as a base. Which one would it likely do? So look at this value and this calculated value, the larger one. If Ka is larger, it's an acid. If Kb is larger, it's a base.